You need a village to raise a scientist. You need a village to raise an academic. It is not a one-man job. And if you are here tonight, or online, or at least here in spirit, then you are part of coronal mass ejections, a big thing that happens on the sun. And during that explosive event, you accelerate a lot of particles. And those particles can reach Earth. If they reach Earth, they can be measured on ground level or in the atmosphere as even higher levels of radiation. So we have these particles, they propagate through space, they reach our Earth's magnetic field. Some of them can penetrate the magnetic field, then they reach our atmosphere, and they essentially make our atmosphere and space radioactive. So that's already the answer to the question, why do we study these particles? And I can show that again with a second experiment. So we repeated the same experiment, the balloon experiment, but you take your Geiger-Müller, the Geiger counter or the Geiger-Müller counting tube, and you pack it in your luggage on the plane, on the hand luggage. You make sure nobody sees you, you switch it on, and you can measure the radiation levels on a flight. So this was one flight we did in 2019 from Johannesburg to Addis Ababa and back. I was not carrying it, I had the student carry the detector. And you get really interesting data. So for those of us, a lot of us are frequent flyers. The Geiger counter data is at the top panel. The pressure data is actually much more interesting. So we also have a little pressure sensor on board. So if you look at the red curve, that's the atmospheric pressure at Johannesburg. So 90 megabar, or if that unit is correct. And you can see what happens if they close the doors of the plane, so they pressurize the cabin. You can see a little bip in the pressure. If the plane takes off, remember this is the cabin pressure, so inside the plane, not the outside pressure. But even in the cabin pressure, you can actually see the pressure drop. When you climb in altitude, you can see when the plane reaches cruising altitudes, and you can actually see it changing flight levels, so as you're flying. So it's actually pretty cool to look at the data, and of course at the end you landed at Addis Ababa. The pressure is much lower because Addis Ababa is almost 3,000 meters above sea level. So that's the pressure, so it shows what happened on the plane. If you now look at the data, the red dots, that's the Geiger counting rate from Johannesburg to Addis Ababa. So same as the balloon case, you have low levels of radiation on ground level. When the plane increases in altitude, you can see the intensity of the radiation increases very, very quickly, and then it's almost constant during the cruise altitude, and then it drops again when you land in Addis Ababa. Now, if you look at the physics and you start looking at the details, we can find out a lot of stuff. The one is, of course, the intensity depends on the height or the amount of atmosphere on top of you. So if there's less atmosphere on top of you, you have more radiation. The atmosphere shields us. And the second thing that's interesting is if you fly from Johannesburg to Addis Ababa, the intensity decreases because you are flying towards the magnetic equator, and the magnetic equator shields us much more efficiently from radiation. So the Earth's atmosphere and the magnetic field protects us from the radiation caused by these particles, and that's why if you're on ground level, you needn't worry about radiation. Yeah, if you're interested, and sometimes when I land in somewhere like Ethiopia, I manage to switch on my cell phone, you get 25 messages from your parents, because you'll see there's a little weird data point, so the intensity dropped, and then we stayed at a constant altitude and then decreased. So we flew over the Ethiopia Airlines plane that crashed, which was pretty scary. And Anyway, so these particles make the atmosphere radioactive. And of course, if you're a frequent flyer or a pilot, you're flying every day, every second day, you're exposed to much higher levels of radiation. And in most countries, flight personnel, pilots, everyone working on the plane, are defined as radiation workers. So their levels, the levels of radiation they are exposed to must be monitored, and they have certain limits which you cannot cross. So that's one reason why we need to look at cosmic rays. For flight personnel, it's a cancer risk, essentially. Now, what happens if you move higher up into the atmosphere? So if you're on the International Space Station, and this is a picture of it, you're above the atmosphere of the Earth, so you don't have the shielding from the Earth, but you're still in the magnetic field of the Earth, so you're still in the geomagnetic field. But if you're an astronaut on the space station, the atmosphere is not there to protect you, so the level of radiation that astronauts are exposed to is much higher than we would allow any, even radiation work on Earth to be exposed to. So in all the crew modules, it's filled with radiation. The radiation levels get monitored in real time. It gets sent back to Houston. And if there's an event on the sun, or there's a possibility of such an event that might produce additional radiation, they do have some countermeasures in place where the astronauts can essentially go to a shelter in the space station where they are more protected against radiation. But they are still in the Earth's magnetic field, so it's not probably not a life-threatening scenario. However, if you go even further from Earth, there's Earth, and if you're an astronaut on the moon is only inside the Earth's geomagnetic field for a small percentage of its lunar orbit. You don't have any protection from the atmosphere or the magnetic field. So if you're an astronaut on the moon, you're exposed to all the radiation, and if the sun does something weird, it accelerates particles. If this extra radiation reaches you, it might really be a serious scenario. So these are not snakes. These are the energetic radiation particles accelerated at the sun. And there is actually historical evidence for something like this happening. So on this graph, which I like a lot, it's the best propaganda graph you can get, it shows data for the last, or for 30 years from 1985 all the way back to 1985 to 55. These thin vertical lines everywhere, they show the biggest solar energetic particle event. So this is the biggest events of radiation produced by the sun. If the line is higher, it's more serious, so more particles were accelerated. Now, on top of this figure are a couple of small dashed lines labeled A11 to A17, and that's the Apollo missions, so the moon missions. So Apollo 11 was Neil Armstrong going to the moon, Apollo 17 was the last mission, and what you can see is exactly between Apollo 16 and 17, there was one of the biggest solar energetic particle events in the last 50 years. So the question, so the astronauts were lucky. It happened between the two Apollo missions, so no astronauts were in space, were not exposed to this irradiation. The question is, what would have happened if they were exposed? And the consensus is it would have been definitely a mission-ending event. So the astronauts would have been subjected to sufficient radiation that they had to drink their sodium pill, iodine pills, get back to Earth as soon as possible before they get radiation sickness. So we have some historical evidence that this does happen. So just keep that in mind as well. So now, how do we contribute to solving all the radiation problems I mentioned previously? We contribute in 3 ways: theory, modeling, and measurements. And I think we are the only group doing any type of cosmic ray research that actually have expertise in all 3 parts. And I think that's what makes us such a very good and strong group. So I'm going to mention a little bit of what I actually do. So I don't make nice pictures. I actually do work. But the work is only interesting for a very small fraction of people. Anyway. So just to touch on the theory a little bit, this figure makes me very excited. It also makes Eugene very excited. So if you want to know more about theory, please go to the Botanical Gardens next Wednesday, I think, when Gina has his talk. What this shows is a simulation from Addis, who I lost somewhere, that shows one of these solar energetic particles propagating in a turbulent magnetic field. So one of the things that is generally a misnomer is that space is a vacuum. Space is most definitely not a vacuum. It's filled with a plasma. If something happens on the sun, these particles have to move through the plasma from the sun to Earth. And it's a very special and interesting type of plasma because it is turbulent. So a turbulent magnetic field influences particles in very peculiar ways, and you can see this weird orbit. So all the physicists should know that a charged particle performs a circular orbit. If you have turbulence, you get this weird, wonky, perturbed motion. So we study the fundamental physics of the transport in order to couple the motion of the particles to the turbulence. And if you do that, you can go through the next step, which is to get an equation that describes the evolution of these particles from their creation at the sun until they reach Earth. There's a lot of terms in there, these coefficients d and the big D over there, that we can derive from theory that couples the particle motion to the turbulence. And if we have such an equation, in principle, we can predict how the particles should move in space. So if you have your equation, then you take off your physicist's hat, you put on your applied mathematics hat, and you need to solve this equation. You can only solve it numerically. So I am some of the weirder people that like the numerical part of it. So this is one example, which is a very simplified example of how to solve this numerically. So you write out all your numerical methods, and you take off your applied mathematics hat, and you put on your computational scientist hat, and you write a code to solve your equation. This is very badly written, so the people from computer science are not allowed to look at the details. And depending on the code and how complex it is, either you can run it on a laptop, or you need to go to a cluster, you solve the equation. It is very boring, but at the end you get out a picture, which is quite nice. So this is some example solutions of stuff that we can do, which I think is very unique in the world. So I'm not going to go into super detail. Maybe for the physicists, I'll just give a highlight. So this figure shows the ecliptic plane, so the plane of the planets. So you're looking from the top, the sun is in the middle, all the planets orbit the sun. So Earth in this model is this green square, and all these other colored squares are spacecraft, or the constellation of spacecraft as it was on this date, which I think was 17 April 2018. And the contour plot is our model solution. So there was an event on the sun, somewhere there. We modeled the evolution of these particles as they move into space, and we can put all these spacecraft that measured the event into our model, and we can create synthetic data, like on the right panel, which shows what a spacecraft would have measured, the intensity, as a function of time. And there you have all the spacecraft listed. We have spacecraft at the moment. We are very lucky. We have spacecraft at Earth. We have MAVEN at Mars, Stereo A, Parker Solar Probe, Solar Orbiter, Bepi Colombo. We have many spacecraft that we can use inside the heliosphere. So we do this. We solve the model. You look at the output of the model. You compare it with the data. And if the data and the model compares well, then you know you understand the problem. If it doesn't compare well, something is wrong and you need to fix the model. So that's one example. We can do this for many different cases. This is a second example where we looked at the intensity along the trajectory of the MAVEN spacecraft that went to Mars. So again, just a typical example of what we do. The red curves are the model solutions, and the blue, in this case, is real data taken from the spacecraft. And what you can do with such a comparison, we learn a lot about the fundamental physics. And sometimes you see parts like this over here where the model does not agree with the data, and then the question is, why is this? Which we don't know. And then lastly, some examples. This is from Ruan's PhD. That shows you can also make the model more realistic. So you can have the perfect world, that's the physicist's world. It's a spherical chicken joke. And in the right is the real world, where you can add much more physics and you see how the real world behaves. Okay, so we also do measurements, and that's maybe more interesting. We don't have spacecraft. Unfortunately, we don't have our own detectors even on CubeSats yet. We are working on that. We can measure cosmic rays still, however. So one of the projects we started a while ago, it took a while to find the acronym, High Altitude Radiation Monitor, HARM in English, but the English is irrelevant, so I think all of the physicists should remember the name. So that's Harem Mural, which passed away a couple of years back. So we decided to name the detector after him. There is a version of it. It's in front here if you're interested. Built on the campus. So everything in here was built by instrument makers, and Corey did all the electronics. So this is based on the German design, completely built in-house. We did some modifications to make it better. And we've tested it pre-COVID already. So we had this detector on a couple of flights. So there's a flight from Johannesburg to somewhere in Germany and back again. And the difference between this detector, the normal Geiger counter, is you can actually measure the absorbed radiation dose in meaningful units. So you can measure microgray per hour during a flight. We have some examples, we know it works. We need to deploy it still and get more data. This specific version is the version that is owned by SANSA, the South African National Space Agency, and the idea is to have these on many flights in the next couple of years to measure how much radiation our pilots are exposed to. This is a measurement that's not been done before. Then you have to go to the lawyers, and you have to create policy to regulate this when you can measure it. So there's some nice data. So for instance, the second flight from Germany back to South Africa, there's the data. You can see the radiation level jumps up, and then it has this nice decrease before it increases again, and this is exactly when the plane crosses the equator. So you can actually see the equator shielding you from the radiation. And near the end of the flights, it always picks up a little bit. That's because the plane burns off the fuel, it gets lighter, and it goes up to 40,000 feet or something like this. So we're in the process of hopefully getting more data, and we're also in the process of building models that can predict these radiation levels at altitudes. Then there's a photo of two very handsome gentlemen next to a detector, and I always like to show this example, especially if there's an important functionary around. This is one of our mini neutron monitors. So this is a neutron monitor that can measure cosmic ray levels on the surface of Earth by measuring high energy neutrons. This whole detector is designed and built on campus. So again, Toit instrument makers, they manufacture the whole body, the lead inside everything. The electronics was designed through a couple of master students and overwintering students at Sinai in Antarctica, and the final assembly and the electronics build is done by Corey in the physics lab. So these devices are, let's say, proudly South African and proudly Noordwes-Universiteit, and they've been deployed at the moment to 6 continents. So there's a bunch of them in different countries, and 3 of them installed at the moment also on research vessels. So we continue to measure these particles as well. Okay, so that's the boring part of what we do. Some more nice pictures. What about the future? And I think the future for space science is internationally very bright. At the moment, if you Google, if you have your phone on, Google Artemis 1, you will find this picture here. It's a picture of the Space Launch System that is currently standing upright in Florida. It will be launched on Monday, the 29th. and that's the first step of taking astronauts back to the moon. So this is Artemis 1. It will be uncrewed, so there will be no people on board. So the only thing that goes to the moon is the Orion capsule right at the top, and that will be filled by a bunch of detectors and this dummy. So the dummy is rigged with all the radiation measurements or the radiation detectors. It will launch on Monday. It will spend some couple of weeks orbiting the moon, making measurements of the radiation levels, and coming back hopefully in one piece. If this is successful, there will be some more shorter-term crewed missions, and then in 2026, if everything goes well, we should have what they say, boots on the moon again. So we will see astronauts in the next couple of years walking around on the moon. But and if you have this, of course, if you have more people on the moon, you have to make sure that you don't have accidents. So you have to make sure that you have a grasp of the radiation levels so you can warn these astronauts in advance. This is only the first step, so internationally there's a lot of work being done. The second interesting thing for us is the Gateway. It used to be called Lunar Gateway, it's now just called Gateway. The first part, this power and propulsion element, will be launched in 2024, and this would be the replacement for the International Space Station. So the International Space Station will be decommissioned in 2030. The Gateway will take its place, but the Gateway will be on a lunar orbit. So that will be in deep space, orbiting the moon, and the idea is to have it permanently crewed. So if everything goes well, by 2030, we might see a permanently inhabited moon and lunar gateway, if everything goes very well. And then we have to make sure that these astronauts aren't exposed to these deadly amounts of radiation. So this is where I think a very interesting application of our model results, and I hope Arik is listening online. He made this figure. So this is a figure that he made for a new paper we were working on. The contour plot is actually our model result, and all the stuff he added on here. And what we use this model result for here is to look at possible scenarios. So what could happen to astronauts on the moon? So there's Earth, there's the moon. The model shows a worst-case scenario, and we use this figure to propose in the current NASA decadal survey. We're proposing a white paper for a mission, a dedicated mission, L4, to actually monitor this part of the sun that will produce the particles that will interact, that are harmful to astronauts. So we're using the model to inform policy, which I think is very interesting. Of course, it doesn't end there. Also shown on the top is some trajectories. These are Hohmann trajectories. So if you want to know anything about Hohmann trajectories, there is Amy somewhere. You can ask her. This is the trajectory of launching a vehicle to Mars from Earth. So there's the outbound trajectory. You launch something from Mars, from Earth to Mars. And this scenario shows that if you need to protect astronauts on transit between Earth and Mars, you need essentially the same kind of setup. So we're also using the model to look at possible worst-case scenarios for astronauts making the journey from Earth to Mars. And yeah, so this is something I would like to see before I retire, and officially my acceptance letter says I retire in February 2050, I think. So by February 2050, I think I'm fairly confident we will have some version of this. It will not be the Hollywood version you see here, but there will be some version of a permanently inhabited base on Mars. I am very confident. One of the big stumbling blocks for this is radiation. How do you shield astronauts against radiation on the journey, which takes 9 months? And how do you shield them against radiation when they land? So it's not an engineering problem anymore, it's now a physics problem, and we can solve problems. And yes, I think the one thing that I like a lot is that for something like this, and this is I mean, most people, including me, if you're in school, you can only dream of something like this happening. I think the nice thing about the international community and the researchers in this room that all contributed to this research means that we are making a very small but still significant contribution to realizing a dream like this. So somewhere in the southern tip of the African continent, some building full of people are helping to inhabit the Mars, which I think is really a wonderful thing. And with that, I will end. Thank you very much. I hope so. It's my first time, I don't know what to do. Thank you.
And then I just need to give this to you. This is you there.
Thank you very much.
Your name there, etc.
Thank you very much. Picture. Thank you very much. Stand or leave? I'll stand. I'm too scared to sit now.
Goeienaand allemaal, Dumelang, good evening. A warm word of welcome to each and every one of you to this inaugural lecture hosted by the Potchefstroom campus of the Northwest University. It is indeed an honor and a privilege. It is our pleasure to welcome into our ranks a new professor, Professor Toit Strauss, a very distinguished scholar, as you have learned, and a scholar who is able to not leave people like myself and including my colleagues from the law faculty and maybe others here, leaving us lost in translation. We certainly were able to learn a few things today about the world of physics. These days, I must confess, I learned a few things from my daughter's experience. She's at high school studying physics, and among other things, of course. And she did pretty well about 2 years ago. And then her marks, suddenly dropped, and I've been very worried, and I just succeeded about 2 weeks ago in finding her a tutor to help, because she's in her matric year this year. And then I began to do a bit of research, and I learned that her past teachers had left the school, and she was being introduced to new teachers. And so her performance was affected by the quality of the teaching. And I can, vouch for that, because when I was at high school, I also studied, physics, not because I chose to, but I didn't have a choice. And I won't tell you how bad I did in my physics. I'm not even sure that I passed the subject at the end. I did, get my matric, but I was certainly not good at physics in any way. But the moral of this little story that I'm telling you is that the role of the lecturer or the teacher or the professor, as it is today, is utterly important, especially for a subject like physics. My son is not he's studying law here. He wasn't the brightest child at school, but he got the top award for history, and I thought, oh, well, I also did well in history. We can manage that. But physics is something where you really must have the best teacher, I think. So it's an honor that we have people who can break the complex world of physics into small bites that we can absorb and we can feast on. This really was a revelation, the world of science, the world of space, cosmology. all these things are what, well, it doesn't just make the world go round, but it's making the difference, and it's helping us to understand the universe in ways that we never did before. So we want to congratulate you, and we know in view of your research rating and your research output that you and the team that you work with, many of the colleagues are here, are doing fantastic work that causes the Northwest University to rise in, in the university rankings and be recognized for its high rate of, scientific output. So I want to congratulate Professor Strauss in your midst again. And while this is the culmination of a journey, as you were reminding us earlier, your retirement is only going to be in 2050. So between now and then, to come back to the aspect of measurement, you put it very clearly there. I'm sure the faculty will be measuring your output and the great things you're going to be doing between now and then. It is the start of a new journey in a way. So in as much as this evening is a celebration of achievement, and it is in the midst of all those, or with all of us who have helped you in different ways to get to where you are, it is also an invitation to work even harder and achieve greater things in the future. And you have alluded to that. So I think this is a great example of how colleagues in the sphere of university research need to face the future. See it as a greater challenge, and you've given us an outline of some of those proposals. We are very excited about the work that the faculty has been doing, is doing, and with people like you, coming into our midst as fully fledged professors, I can confidently say that the Northwest University is going to reach great heights in scientific research for the foreseeable future. Thank you very much, and congratulations again.
Ladies and gentlemen, just to end things tonight, I just want to concur with Prof. Abalia. Even for our normal natural scientists, and there are many of us here, to look at the type of research that you guys do, you don't have to wear a tie to Toit, and you don't even have to wear long pants or even shoes for that matter, and I know you will appreciate that. But when you go to the moon, I guess you would. But for that reason, I brought my special Stardust tie tonight, and I'm happy to donate it to you if you want to. So, colleagues, that just leaves me to conclude the formalities. And before I do that, I would just like to thank, on behalf of the faculty and the colleagues, to our staff members, Emma, Ashley, Belinda, and Darlene and Dube outside. I don't know where they are. And the photographers here tonight for making this possible. Very warm thanks to you for doing this. And with that, we can close this and we can stand for the anthem. Thank you.